Hello everyone, I am Nasrullah from IBM Research Almaden, and I will be presenting scaling knowledge graph embedding models for link prediction. This work is done in collaboration with Shao and Berthold at IBM Almaden and Chuan from Instacart. GNNs are a powerful tool to learn representation of nodes in a knowledge graph. The embedding of a node is learned by aggregating k-hop information of its neighbors. The number of hops depend on the number of GNN layers. Moreover, real-world knowledge graphs are large, having millions of nodes and edges. The k-hop dependency and large graphs make training of knowledge graphs challenging due to high computational cost and memory requirements. To reduce the training time, training needs to be performed in a distributed settings. We propose a model for distributed training of GNN-based KG embedding models for link prediction. We first partition the data using an edge partitioning strategy. The number of workers determine the number of partitions, and then apply neighborhood expansion on partitions, which adds k-hop dependencies of all nodes in the partition. This expansion makes partition self-sufficient, that is, during training, all data required for training is available within the partition, hence reducing the communication between workers during the training. Since the partitions may also be big, we employ an edge mini-batch strategy for training in order to further reduce communication strategy. In order to further reduce the communication, we apply a constraint-based negative sampling strategy, which generates negative samples from within the partition. During the training, only gradients are sharing. The algorithm shows the main three components, which requires high computations during the training. For experimental evaluation, we used a cluster of 4 machines, each equipped with two P100 GPUs, Intel processor, and 762 GBs of RAM. For distributed training, we used PyTorch distributed data parallel library and PyTorch geometric for developing embedding models. We performed evaluation on RGCN. It may be noted that any GNN-based KG embedding model can be used for training. We use 2 datasets, FB15K237, as it is a standard benchmark dataset to show the comparison of our results. The second data is OGBL citation dataset, which has 2.9 million nodes with 30 million edges. For evaluation, we train on 2, 4, and 8 workers in distributed settings. Each worker in all of these settings have same workload per worker. The training is done on GPU. Each compute node runs 2 workers. One trainer process means non-distributed training. We see that in accuracy table, we see that across all distributed training, results are comparable to non-distributed trainings. Hence, in distributed training, we don't see any deterioration of results. The scalability results are shown in the plot. The plot shows time per epoch. We are able to achieve a superlinear speedup of 16x with 8 trainers on OGBL dataset. The second plot shows the running times of these 3 major components during the training. In summary, we show that our distributed training approach scales without any deterioration of results. We reduce the data communication as our approach does not require any training data to be shared. Thank you.